Alkanols are alcohols, and they are actually referred to be derivative of alkanes. How we do this is that we remove hydrogen atom or atoms depending on the number of hydrogen ion or hydrogen group that are going to be present in that alkanol. Therefore, we can have something that look like this. In this methane, if we remove one of the hydrogen here and insert OH, we will have methanol. Hope you get that. This is just the difference. Therefore, we remove this hydrogen and we set the OH group to it. That's a sample of an alkanol. Okay, here we have methane. We have this methanol, and you recall how we got this. Now, if we do the same thing here, let's assume that we are putting the OH here. That is the hydrogen group there. You see this, if for instance I have two OH group, that is I put one here, I put one here, it can change the name from ethane 1 to diol. We will come to that when we move much deep inside the alkanol. It is also said to be derived from water molecule by replacing the hydrogen ion from water by an alkyl group. Yes, something that looks like this. This is water molecule. This is an alkanol. Here, this R, the general formula for this R is, if you notice, you will see that this thing wants to look like the general formula of alkane, but just that alkane is 2, but this is 1. That is to say, there is one hydrogen shortened when we are referring to alkyl group. This R is an alkyl group. Do you get me? Okay. We are having one hydrogen shortened from alkane for us to have what we call alkyl group. And this N can be any value. We have other members of alkanol, which include methanol, ethanol, propane 1-ol, propane 2-ol, 2-methylpropane 2-ol, ethane diol, propane 1,3-diol. We still have something like propane 1,2,3-triol, and many of that. We classify alkanol into 3: monohydric alkanols, dihydric alkanols, and trihydric alkanols. If you are a student and you're about to write WAEC, continue with what your teacher told you about the general formula for alkanol. I believe that our teacher normally gives us this as the general formula for all alkanols, but here I'm using it for only monohydric alkanol. I know you may be having confusion. Is your teacher wrong? Is your textbook wrong? None of them is wrong. It's just that the most popular of the alkanols is the monohydric. Therefore, we use the general formula of the monohydric for all of them. Let's take when N is equal to 1. This is methanol, and this methanol is a monohydric. It is not actually a dihydric, neither trihydric. Therefore, this formula is actually working for monohydric and not other of alkanol. The diagram of this will look like, I have a simple reason why I changed the position of the O. You know, before it was so that you will not say that this is only how to write this. That means that the OH can be here, the OH can be here, the OH can be here. If you notice this, you see that the O is in V shape in each of the diagram I'm making. Even if I make mistake in the process, always put it in your mind that the O is in V shape. I don't know if you get this. This is based on the shape of molecule of oxygen bonding with 2 atoms, not oxygen bonding with 1 atom. This is oxygen bonding with 2 atoms. This is 1 and 2. Okay, when this thing happens, they always be in V shape. That is why water shape is V shape. Some people call it angular. Some people say it is bent. That is why we are having it in this form. I hope you get that. So don't panic that I put the OH here. I can also put it here. I can also put it here. But one of the beautiful things I want you to put in your memory is how I curved this. What if we have N to be 2? This is ethanol. If I put this O here, it is still going to look alike. I don't know if you understand me here. That means that the counting will still be position 1 and position 1. Just like this one is always position 1. Even if I put this OH here, it's still position 1. Even if I put it here, it's still position 1. That is, look at what I mean here. Both this and this are the same thing, no change. It is position 1, position 1. Therefore, we call it ethanol. Since no matter where you put this OH, you are still having ethanol. But let's try it in when n is equal to 3. Let's face this. Okay, look at what is going to happen. Let me insert OH in each of the carbon in different position. We will have, if you look carefully in this diagram, you will notice that this OH, that is the hydroxy group, is found at carbon number 1 or carbon number 3. But the position here is 1 because 1 is lower than 3. Therefore, we are choosing this. If we go over here, we are going to have the same issue, that this is found in position 2 and position 2. Therefore, is equal. Therefore, we take this as position 2. But this one, we have position 1 and position 3, which is very, very similar to this. Therefore, it gives us propane 1 all. That is, this one that is at position 2 is called propane 2 all. I would like you to do this for when n is equal to 4 and 5 and tell me the possible positions we can see here. This means that alkanol will have what we call position isomerism. This is position differs, even though two of them are the same, but this one differs from them. Then don't forget to do the work I asked you to do for me when n is equal to 4 and when n is equal to 5. When it is 4, we call it but, and when it is 5, we call it pent. In many textbooks, they will tell you that alkanols are classified in 2 ways. One, based on the number of hydroxyl present, and the other based on the number of alkyl group present. One, primary, secondary, and tertiary alkanols. Okay, let's start with primary alkanols. So when we have a monohydric alkanol, alpha carbon, being attached or bonded to one alkyl group only, or maybe bonding to all hydrogen, it is called primary alkanol. Let's look at them. What we mean by the alpha carbon is that carbon that is directly bonding to the oxygen that is bonding to the hydrogen in the OH. I hope you get that. Therefore, this is the alpha carbon. And if you look at this R represents the alkyl group. And it is only one alkyl group that we are seeing here. This R can be alkyl group that is gotten from CnH2n plus 1, or it can even be only hydrogen, because if n here is 0, if you put 0 here, put 0 here, only one hydrogen will remain. Therefore, we can have something that looks like this. This is for methanol. You see, this R here is being replaced by H. That is when n is equal to 0. Okay? This CH3 is this CH3 here. Do you get me? And this CO is this CO here. Do you get me? Therefore, this CH3 can actually represent this. But this is our alpha carbon. This is our alpha carbon. Now, this is the primary alkanols. Let me bring in one more, the propane 1 all. This is our alpha carbon. And this is the same thing as C2H5. That is, hope you get me. Therefore, we can call this propane 1 all because the position of the functional group is at position 1 or the first carbon. Hope you get that. And you see that this carbon is not attached with any other carbon except this. Any of the alkanol that ended in 1 all, it is a primary alkanol. If, for instance, the alpha carbon is bonded to 2 carbons directly, we can actually call that a secondary alkanol. Let me demonstrate this. Look at this carbon very well. This is bonded to an alkyl group and also an alkyl group. Now, let me use different signs to demonstrate this so that I can differentiate this R. The R can be of the same alkyl group or different. But what I'm trying to say here is that the carbon is bonded to 2 carbon or 2 alkyl group here. I hope you get that. Okay, let me demonstrate this. This and this are just the same thing. If we go like this, we are going to have position 2. That is why I spread this to look like this. I hope you get me. Okay, now if this is position 2, it is not in position 1. That means that anyone that is not position 1 is likely going to be secondary alkanol or tertiary alkanol. When we go over to tertiary alkanol, I'm going to give you rule that you're going to use to know when an alkanol is a tertiary or primary alkanol. Then if you are able to remove the two, then the secondary alkanol is not difficult for you to go for. Let's have something that have different R. This one is having the same R, the same alkyl group. If you look at this carefully, you will see that the position of this functional group is not at position 1, as you can see there being explained here or better done here. Now, that is all monohydric alkanols that is not at position 1, that has no derivative, is called a secondary alkanol. Now let's go for tertiary alkanol. Whenever the alpha carbon bonding to the hydroxy group is bonding no hydrogen atom, it is said to be a tertiary alkanol. Therefore, this is an example of how to represent this. Okay, let's put an example. Remember I said that the R can be R1 or R2. They can actually just be the same thing. Let's use the one that are the same thing. I prefer this than this, but any of them you see in your exam, just pick it up. Okay, now for us to name this, we need to label this. The highest carbon atom here is 3, therefore we are having prop. But if we are counting like this, we are ignoring this. Therefore, let's just count like this and ignore this. We are going to have, remember that this is the position 2 that we are seeing this OH. Since we counted like this, we do not include this. This is a methyl group, therefore this becomes a substituent. Now this substituent will be in front of this. We have 2-methyl propane 2-ol. Let me do another one so that when I drop the rule, it will be easier for you to grab. The truth is that your examiner will not drop this diagram in this form. They will normally use this pattern to drop it for you. Hope you know that. Therefore, you need to learn how to convert this to this. It's very, very important. If you have started this video from introduction to organic chemistry 1, I hope you understand how to pull this from here to this. Okay, now let's pull this thing from here back to this. The first, if you look at this, you have CH3, CH3. Therefore, you're having 2 CH3 here. We have, and it is bonding to this C, and this C is bonding to OH, at the same time bonding to this C2H5. Therefore, we will put this thing in bracket to make it easier for us, or we can still put this one in bracket. Any of them we choose is correct. But remember that this C2H5, we can expand this. We will have something that look like this, or better we use this. This will be easier for us to number than this and this. I hope you get that. That's why I need to bring it down to this point. This is the same thing as this. 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 But this one will help us to be able to number the value. When we spread them perfectly, we will have. We can go from 1, 2, 3, 4. We can go from 1, 2, 3, 4. We can go from 1, 2, 3, 4. I hope you get this idea. Okay? Therefore, we are having 4 as the answer. 4 for us is boot. And the positions are position 2 and position 3. And 2 is lower. Therefore, we are having, if you count this from here to here, the position is position 2. If you count it from this position 3, but you are taking the position 2. Therefore, if you count the total number is 4 carbon that are present in the straight chain. And it is called butane. Since it is position 2, we call it butane 2. Since there is OH present, we call it butane 2-ol. Now, when we counted this in this form, from here to here, we ignore this, which is a methyl. Therefore, if we start it, we are going to have. Let's do one more. One more is important. I don't want you to get confused. Don't think that 2, it must be 2. Now, let me introduce one where we have scattered value, because when we have the scattered value, it will give us a different name. Let's go. What I mean by the scattered value is scattered R. This R and this R is the same. Hope you get that. But now let's look at the one that have, this is a different R, different R, different R from one another. Let's look at it. This, we can reduce this to look like this as, watch, 2, 2, 3 will give us 7, 1, 1, 1 will give us this 3. Hope you get that. Okay, now let me introduce this C here. It is going to be bonding with this. The OH will be there. Expanding this, we will have. Let me use the line on so that it will spread apart. The position of OH is either at position 3 or position 4. Therefore, we are taking the position 3 rather than position 4. And the total value we have here is 6 carbon in a straight chain. So we are having hexane 3-ol. But when we counted this thing in this form, we did not count this. So this is a methyl group found at position 3. or position 4, but we are taking position 3 because this is the least value. So we will have 3-methyl hexane-3-ol. Now I want to bring out something for you to see. If you look at this very well, you see that the position here is the position here. If you look at here, the position here is position here. If you also look at here, you see position here is position here. I hope you get that. That is to say, the position of one of the substituents must be equal to the position of the functional group, which is the 3-ol here. Here is the substituent. One of the substituents must have the same value as that. And that substituent must be of alkyl group. If you get this value, you will understand this easier. Now, look at the general way of distinguishing them. We will have it like this. Note, this primary alkanol behave differently from secondary or tertiary alkanol. For instance, primary alkanol oxidizes in the presence of potassium permanganate or potassium dichromate to give us alkanal, and further oxidation will give us alkanoic acid. But this oxidizes directly to alkanol, but this does not oxidize at all. I hope you get that. Now let's go for dihydric. Here we are actually looking at the number of hydroxyl present per molecule. Therefore, if it is 2 hydroxyl that is present, we call it dihydric. That means that the word dihydric actually means 2 hydroxyl group present. Okay, let's look at this general formula. Remember that I told you that if you are trying to apply the general formula that is being given to us in our textbook, it will not work because I have actually demonstrated that for you. But let's apply this general formula for dihydric alkanol to see that this formula is different from what they gave us or what they gave us in some textbook on our teacher. We will not have n is equal to 1 because it will look like this. We don't have this. Let's continue with n equal to 2. So we will have, using diagram of the structure, we will have. So we insert the OH here. The position of this OH is at position 1. The position here is now assuming as position 2. And since it is only this, we can just call it ethane diol. But for proper numbering, we call it ethane 1,2-diol. This is the first member. Okay, we can also have something in this nature when n is equal to 3. So we can have something like this. Please, this is 2. Okay, so if we use the structure, we will have, filling up the hydrogen, we will have something that look like this. Or, hope you see the difference. Okay, we can name this 1, 2 and name this 1, 3. This is position isomer. I hope you get that. Now let's look at trihydric alkanol. The word 3 already points of 3. That is the word tri. Therefore, we are looking at the alkanol that has 3 hydroxyl group present per molecule of the alkanol. I'm only going to name one. I will leave the rest for you to try. This is called propane 1,2,3-triol. Another name for it is glycerol. And we normally get this whenever we have a saponification reaction. This saponification reaction make use of oil and sodium hydroxide. It is a hydrolysis reaction where this oil is being converted to an organic salt, which we know as soap. And the byproduct is always propane 1,2,3-triol. We call it glycerol. Some people call it glycerin. Any of them that you see, it is the same propane 1,2,3-triol they are calling. Another one I can just put over here for us, you might not be seeing it in your textbook, but it is still something that we can call up to, is butane 1,2,4-triol, or we can even have butane 1,2,3-triol. I know that I said that I'm only going to give you one example, but I have given you 3. Therefore, your knowledge, I believe, is increased here. You can try something in the nature of when C is more than 4, something like C is 5, C is 6, and tell me the possible isomers we can get. Ethanol is the second member of monohydric alkanols as homologous series. It is mostly said to be alcohol Its molecular mass is approximately 46 gram per mole. We can prepare ethanol by the following method. Hydration of ethane. We do this by using either tetraoxophosphate 5 acid, or we use tetraoxosulfate 6 acid. This is how the reaction looks like. Another method is fermentation of carbohydrates. The question might even be what we even mean by the word fermentation. This is actually a gradual or slow decomposition of larger molecules into smaller molecules using catalysts like enzymes. That is what we mean by the fermentation. This can be fermentation of carbohydrates where we have something like sugar or starch. From sucrose, we will have something that look like this. This is the first stage of the reaction from sugar. Okay, this is sucrose, which is the sugar. This is glucose, and this is the fructose. But this is the sugar that we use at home. The sucrose you are seeing is the sugar that we're using at home. Okay, what happened here is that this invertase is actually gotten from a yeast that converts the sugar from sucrose to glucose and fructose. And inside the yeast again, we also have another catalyst or enzyme called zymase. This invertase is an enzyme, another one that will convert this glucose to ethanol. This is from sugar. Therefore, this glucose will be added by an enzyme called zymase that will convert it to ethanol, or that will convert it to ethanol and carbon 4 oxide. We can still make use of starch. If you are making use of starch, it means that you need to look for starchy food, something like potato, cassava, maize, and this is actually what is being used in industry, that the brewery industry. That is what they normally use in order to get their alcohol. If you are trying to get this ethanol from starch, what we do is that we're going to extract the starch from potato, yam, cassava, maize, sorghum, depending on the starchy food you want to make it. Sometimes in question they can ask you to write how to prepare or how to manufacture ethanol from potato. Therefore, the little thing you just need to let them know is that we extract the starch from potato, cassava. It can be sorghum, it can be maize, it can be yam, and you do this by crushing and cooking for a while. Then that will appear. Then we are going to add a malt, and that malt contains diates. So the diates will help us to convert the starch to maltose. After this, a yeast is being added in order to convert this maltose to glucose. And the yeast contain an enzyme called maltase, just like this is an enzyme here too. Okay, and this maltase converts this maltose to glucose. This tells us that maltose is a composition of 2 glucose, whereas sucrose is a composition of glucose and fructose. The same enzyme contain what we call zymase, and this zymase will act on this glucose to convert it to ethanol. So this is what we are going to have, and if you compare it with the sugar only, you will notice this. Zymase is used at the last stage for the two. Hope you get that. That means that zymase is an enzyme that converts glucose to ethanol and CO2. Hope you get that. Let us look at the physical and chemical properties of ethanol. Most alcohol are liquid, and they are mostly colorless. By color, they have these characteristic smell, a particular unique smell for themselves. And if we are tracing that ethanol, the liquid is actually a volatile liquid and combustible, and it can also be intoxicating based on how much you take in of alkanol, mostly the alcohol. They are soluble in water, and the boiling point is a little bit higher than other alkanes, alkyne that have the same number of their molecular mass. Yes, it is a non-electrolyte, and when we check the density, it is less dense than water. Let's look at the chemical properties of ethanol. I want you to know that as the alkyl group increases, the boiling point increases in alkanols. And also, as alkyl group increases, the solubility will decrease. I need you to also know that if we have increase in hydroxy group present, then the solubility increase, the boiling point also increase. But increase in alkyl group will reduce the solubility of those alkanols, not ethanol, those alkanols. That means that if we have something like ethanol and ethane diol will have a higher boiling point, will also have a higher solubility rate compared to normal ethanol, because ethane diol has two hydroxy ion there, because the two hydroxy ion is going to contribute a higher hydrogen bonding compared to normal ethanol that has only one hydroxy group. Hope you get that. Now let's look at the chemical properties of ethanol. It burns in air or oxygen with a pale blue flame. Nearly all alkanol does that. Hope you get that. Okay, it is dehydrated to ethene when treated with concentrated tetrodosulfate acid at 180 degrees Celsius in 2 stages. And I want you to know that this is also a laboratory preparation of ethene. And these 2 stages have something I want to chip in for you. If, for instance, we still have more of this can react with this, and the acid will be recovered. But if we do not have the excess of ethanol, then this will split to this. Okay, let's go for the third point. It forms a sweet smelling ester in a esterification reaction called ethyl ethanoate. This reaction is called esterification. Looks more like neutralization reaction, where this is the acid, this is serving as the base, but here it's not a base, it's called alkanol. And just look at it, forms water from H and OH. Hope you get something here, but it is not neutralization reaction. There are so many reasons why it is not neutralization reaction. Neutralization reaction occur on its own, but this requires a catalyst, mostly concentrated tetrodosulfate acid. And this is endothermic reaction. That means that it requires heat for it to happen. Whereas in neutralization reaction, it gives out heat. It does not require any heat, rather gives out heat to the surrounding. We call it exothermic reaction. Also, there is a presence of alkanol here for esterification reaction, but in neutralization reaction, there is a presence of base. Despite that two of them have this OH present, but it's not all neutralization reaction has OH, because we can have something that look like calcium oxide reacting with any acid to give us water and salt. I hope you get that. Okay. This reaction is actually a reversible reaction. But in neutralization reaction, we don't have a reversible reaction in between acid and base. So let's go for the next point. Ethanol, being a primary alkanol, is converted or oxidized to alkanal, then further to alkanoic acid, where the alkanal of ethanol is ethanol, and its organic acid is ethanoic acid. Therefore, we're going to show this in their stages. You give us ethanol and water. This is oxygen gotten from this potassium heptaozo dichromate 6. In the further reaction, the oxygen from potassium heptaozo dichromate 6 will convert this to be ethanoic acid. This is an oxidation reaction. I want you to know that this is an oxidation reaction because oxygen is being added to ethanol to give us ethanoic acid. Let's look at the uses of ethanol. It serves as a starting material for chemicals like ethene, ethanol, ethanoic acid, and ethane. And we actually use it as well, even in racing cars and rockets. And it is serving as a solvent for production of perfumes, soaps, dyes, drugs, varnishes, and oil. It's actually used in manufacturing alcoholic beverages like beer and vodka, etc. It is used as preservative for biological specimens due to its low freezing point. It is used as antiseptic to sterilize wounds in methylate spirit.